Welcome to qnawire.
In this problem, we have block 1 on an inclined plane of angle alpha, and it's tethered to block 2, which is hanging over the edge. If we draw the free body diagram for block 1, we have the tension from rope 2 pulling it up the ramp this way. Our normal force is normal to the ramp surface, so it's this way. The force of friction is opposing the motion, so if block 1 is going up the ramp, then the force of friction is pushing this way. And then we also have our force of gravity downward. Since the angle of our ramp is alpha, we know this angle is alpha. And that means by trigonometry, this must be equal to mg sine alpha. And this side must be equal to mg cosine times cosine of alpha. Now to solve part A, we need to notice that even when block 1 is moving at constant velocity, its acceleration is 0, and so its net force is 0. So we have the sum of the forces is equal to 0. And since it's moving in this direction, we know the sum of the forces in that direction is equal to 0. So what we need to do is decompose all our forces into the ramp direction, which I'll just call the x direction. And then this can be the y direction. And so we need the x components of all our forces. We're going to sum them up and set them equal to 0. That's the condition for a constant velocity block sliding in this direction. So we know that the tension points in the positive direction, but the force of friction points in the negative direction. Also, the contribution from the normal force will point in the negative direction. Oh, actually, sorry, I just got confused. The normal force is in the y direction only. It's the x component of the gravity force, which we'll be considering. And so when we set this up, we will have this implies negative force of friction. I'm pulling the negative out of the force of friction because I already know it must be negative. So when we calculate this, we have to remember not to make it negative again. And we're going to subtract m1 times gravity times sine of alpha, which is the component here from the gravity. And then we're going to add in the force of tension, which is purely the force here, which is m2 times g. That tension gets transmitted all along the rope. So T is equal to m2g, and it's positive because it's pointing in the positive x direction. This is equal to 0 because the sum of the forces is equal to 0. Now, the force due to friction when the block is moving is equal to the coefficient of kinetic friction times the normal force. In this case, the normal force is equal to this component, so it's mg times cosine of alpha. Like that. And then whenever you add this in here and then solve for m2, you get the final result, which is m2 is equal to mu k m1 cosine alpha plus m1 times sine alpha. I also cancel the factor of g because each term shared it. And that's the final answer for part A. For part B, it is very similar, except in this case, the block is moving downward. And so the tension is going to be exactly the same. The contribution from the gravity is going to be exactly the same. The only difference is that the contribution from the friction force is going to be opposite in sign. And so whenever we write this down, we can pretty much borrow this result here, except this term has to change sign because this is the term that came from the coefficient of static friction. Or kinetic friction, rather. Kinetic. And so we can say that m2 is equal to negative mu k m1 times cosine alpha plus m1 sine of alpha. Notice this term didn't change sign. The only thing that changed was this. And so that's the final answer for part B. In part C, the block is no longer moving, so we have to replace the coefficient of kinetic friction with the coefficient of static friction. And we also need to find a range of values. And so in this case, the range comes from block 1 sliding up versus the block 1 sliding down. Those two cases will produce the range of values. We still need the sum of the forces equals 0. because the block is still not accelerating. And so because of that, we can borrow these results here, except we need to make a few replacements. And so we'll see that the range is from m2 is equal to negative mu s. I'm pretty much borrowing this result, except I'm replacing the coefficient of kinetic friction with the coefficient of static friction. But everything else remains the same because we still have these contributions from those forces. So that's the lower bound for M2. If M2 is less than that, then the coefficient of static friction cannot stop the block. The block has to move at that point. And then the higher value is this value here, except we need to make that change here. So M2 equals mu s times M1 cosine alpha plus M1 times sine of alpha. And that's your range. And that's the end of